thank you very much for all of your answers to the little questionnaire the other day. That was extremely helpful. We are working to implement several specific good suggestions that people gave. For example, we've swapped one of Amal's lectures and one of Xavier's so that we don't have two lectures by the same person on the same day anymore. That was one great specific comment. One thing that poll asked was, what about Coq background and how fast should I go in these lectures and so on? And naturally there was a wide spread of response. But the modal response was either I've done a little bit of Coq or some but not too much. So a few people, none. Quite a few people, a little bit. Not so many people, more than a little bit. And the modal response to how fast should I go was, nevertheless, go pretty fast so we get to more advanced stuff. So what I'm going to do with those numbers is kind of compromise. I'm going to make today's lecture reasonably fast, so I'm going to try to get through 3 or 4 chapters. They're all fairly easy stuff, and I won't just skim over them and say the keywords. I'll actually talk about the trickier parts. And you should ask questions as much as you want, and then we'll get as far as we get. But I'll try to get through that material reasonably quickly, recognizing that you have a little bit of time until the next lecture, one whole weekend day, to consider the exercises from those chapters that we'll be going through fast. And then I'll slow down and do the next few chapters reasonably quickly. So that is to say, these lectures will be aimed at anybody coming to Coq even completely fresh. Those of you who are completely fresh will need to work a little harder to stay caught up, but you should be able to. Those of you who are experts, and for present purposes, let's say that an expert is someone who either already has worked through the whole Software Foundations material or could have written it better than me. So everywhere from already worked through it and up. These lectures are not for you. Sorry, but can't please everybody. So if you're in that category, feel free to not come. There's no reason to have people here and bored and just reading email. It's better for all of us if you just take a break and go work on problem sets from somebody else's lectures. And I won't feel insulted. In fact, if you want to get up now and go someplace else, I won't feel insulted at all. There will be new versions of the Software Foundations material from time to time. For example, I made a new version 5 minutes ago. The new version is not very different from the older version. I'm not doing major moving material around and things like that. But I am slightly polishing the, tidying up typesetting mistakes and slightly polishing explanations and things like that. So you may want to grab this version before you go on with the next exercises, and I will alert you when I publish new versions that you should grab instead of the ones that you're using. For the next few chapters especially, there are far too many exercises to actually work all of them, even if you did nothing else between now and the next lecture on Monday. So I have tried to carefully mark recommended exercises. You can even probably skip some of those because some of them are about functional programming, and you probably could do that in your sleep. Excellent. Somebody taking me up on my offer. Have fun, whatever you're going to do. So there may be a few recommended exercises that you can even skip, but I think if you do all of the ones that have to do with proofs, that will give you a reasonable overview of, it will give you a reasonable depth of intuition about what we've talked about today without taking too much time, I hope. Okay. So diving in, any questions to begin with about the last chapter or anything? Okay. So the basics file was about kind of completely simple functional programming and quite simple inductive proofs and a few other little tactics about simple recursive programs. And our job in the next 2 or 3 chapters is to build up more experience with functional programming, which won't surprise any of you, and a little bit more experience with a little bit more sophistication with proving more interesting things. And that's what I'll focus on. Okay, so the chapter lists.v, and here I'm showing you a very abbreviated version of the HTML for that file, is about programming with more interesting data structures, but without polymorphism. And then in the next chapter, we kind of redo all the same stuff, adding polymorphism. So this is the non-polymorphic version of lists. The functional programming part won't be surprising at all. It's just showing you kind of the Coq syntax for the way we do these things. The type of natural number pairs is defined as a data type with one constructor. The constructor's name is pair, and its type is it takes 2 numbers and returns a natprod. And we can define functions on those things by pattern matching, and we can introduce the usual parentheses, comma notation for pairs via Coq's notation extension mechanism. By the way, those of you that are going to be using Coq in your own work, I have a word of advice for you about notation. What notation does is it extends the Coq parser. So Coq has this kind of fancy extensible parsing technology. However, although it's a little bit fancy internally the way it works, what it can actually do for you is not all that fancy. And if you try to go nuts with notations, you will drive yourself crazy fighting with the parser. So my recommendation is to do as I do here, which is to make very light and selective use of notations, and mostly just live with the kind of ASCII prefix style bare concrete syntax. Okay, pairs are one instance where it would really be annoying if you couldn't write, for example, pattern matches like this. So we do go to the trouble. Okay, then lists. Lists, of course, are just like natural numbers. That is, they have a 0 and a plus. But the 0 is, the 0 is called nil instead of 0. The plus is called cons instead of plus, and it's annotated with a number. Okay, so lists and unary natural numbers are almost the same thing, just modulo an annotation on each cell. And here, again, it's worth doing a little bit of notation hacking. And note that Coq's notation mechanism is smart enough to handle multiple arity, like brackets, comma, 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 close brackets kind of notations. And as usual, as you would expect, we can write functions like repeat and length and append and head and tail. So nothing too surprising there. Now, we can redo the story that we did about numbers, about proving things about lists. And because lists are just kind of slightly generalized numbers, the proof techniques involved are not all that different. So as with numbers, we can prove some things just by reduction, just by definitional equality. So for example, this little property about nil happens to just come out by reflexivity because append, which is written plus plus, is defined by recursion on its first argument. Its first argument here is a concrete list, and so we can just compute it away. In other cases, like the second thing up there, we need to do a little bit deeper analysis, but we don't need to recurse through the list. So this one we can get just with destruct. But to prove interesting things, we need induction. And induction on lists works basically the same as induction on natural numbers. So it says working class there. Shall I take 2 minutes to actually work it in class, or shall we skip over it? What do you think? Let's have a vote. I like votes. How many people would like to see spend a couple of minutes actually doing this proof together? Quite a few. Okay, let's do it. Okay, that is not the right version of that file, I don't think. Oh, yes, it is. Okay. Apologies for the hide in advanced garbage. I'm still slightly working out the hackery of getting all the different versions to look beautiful. So let's work this together. What do we do first? Intros is always a good thing to do first when you have a proof with a theorem with hypotheses, which most interesting theorems have. So what shall we intros? Well, I guess L1 and L2, those are the lists that we're working with. By the way, what are we showing here? We're showing that the length of the append of two lists is the sum of the lengths. So we have the two lists, and there's nothing else to intros. There are no more hypotheses. Now what? Yeah, we're going to have to do induction on something, because what else could we do? We could try destruct, but I think it's clear if you think about this that it's not going to, we're not going to get away with proving this with just destruct. So we're going to have to do induction. So which one should we do induction on? The left one sounds better because that follows the structure of the definition of append. So induction on L1. Okay, help me remember the syntax for this. As, and then we don't need anything for the zero case, but for the non-zero case, maybe L1 prime would be a good name. Okay, so now we have to prove the zero case, first subgoal. How shall we do that? I'm going to leave out the case tactic just to go faster while we're doing this together. Okay, does simple get it? Ooh, it does. And by the way, if simple gets it, then reflexivity by itself. Oops, sorry. Reflexivity by itself builds in a use of simple. So reflexivity will get it as well. Okay, now the interesting part. So we need to prove the induction step. And we're given an induction hypothesis about, let's see. Yeah, so our variable names are all screwed up. Why? Right, so because I was going fast and you guys were just letting me do it, I forgot that lists have a head and a tail, and we need a name for each of them. Okay, so let's try that again. So reflexivity again works for that. And now let's see if the names are better. Yes, okay, so the induction hypothesis is about L1 prime, the tail of the list, tail of the original list, which is X consed onto L1 prime. And now we have to show this. So how shall we start? Simple is usually a good way to at least see if you can make progress. So if we simplify the conclusion, then what it turns into is successor of one expression involving length and successor of another expression involving length. So in order to show this, what do we need to show? Exactly the induction hypothesis. So this was a pretty easy one. So how do we make use of the induction hypothesis? We could do rewrite, yes. And which direction should the arrow go? Either, actually, because we just need to make the two sides of the conclusion equal. So let's try it this way, for example. And it's called IHL1 prime. Oops, thank you. And now have we got it? Oh, it looks good. So reflexivity, oops, should finish the proof, and it does. And now we say QED, and it takes us back to the top level. Okay, so, oops, is that what I meant to do? It was what I meant to do, but it wasn't the tab that I wanted. Drat. Okay. All right. So we did that. So we can go on with standard functional programming. So we can define options. Options are often useful in Coq because all Coq functions have to all recursions in Coq have to terminate. If you have a function that isn't naturally total, one thing you can do is make it return none when it wants to be undefined, and make it return some of something when it wants to be defined. So for you Haskellers, these are just and maybe. Is that right? Sorry, just and nothing, excuse me, and the type is maybe. So index, for example, can take a number and a list and return a nat option. So nothing too surprising there. The one thing to look at is we can rewrite that one up there this way using an if expression. It may surprise you a little bit that we can use if, given that we defined Booleans. They aren't built in. So what does if mean? If actually works with any two-constructor type. So it just distinguishes whether we're in the whether the scrutiny is tagged with the first or the second constructor. Okay, and that's it for the lists file. There are some exercises to try, but should not surprise you very much. Any questions? Okay. So the next file is called poly, and it's about polymorphism and higher order functions and stuff like that. And once again, the main thing we need to do is just look at what the concrete syntax is, because the concepts should be unsurprising. So here is the definition for the type of polymorphic lists. And the way to read this is that list is a family of inductive type definitions. So for each x, for each type x, there is an inductively defined type list of x with constructors nil and cons. Notice also that the types of the constructors change. So because we're defining a family of inductive types, each of the constructors becomes a family of constructors, one for each type family. So nil, for example, now has type for all x, list of x. Okay, so we don't see that in the types of nil and cons in the declaration because we don't need to. It's written once and for all out at the front. Okay, and now we can write polymorphic functions, and the way we do that is by adding an extra argument I shouldn't say of type, I should say of kind type to keep the levels distinct. But intuitively what's going on is just it's an extra argument that's a type. And it shows up in the types of later arguments in just the way that we've been seeing all week. So this is a kind of dependency, although the thing to notice is that it's not quite the same kind of dependency. It's a dependency of term level things on type level things, whereas the dependent pi and sigma types that we've been seeing in previous lectures are dependencies of term level things on term level things, which of course Coq also supports, but that's not what we're looking at here. Okay. There are a lot of type annotations here, and those of you that are used to languages where lots of types can be filled in automatically by the compiler may find this a little heavy. So let's have a little type inference. So for example, on the first line of the definition of app, where is it? we filled in x colon type, and then L1, L2 colon list of x, and then the result type list of x. So could we leave all those off, or almost all of them off? Yes. In fact, we could also leave off the result type, and it would still figure out what it is. So Coq can do the usual kind of type inference on the arguments and results of function definitions. Moreover, it can fill in type arguments as well. So any place where there's a type argument that you don't feel like writing, you can just write underscore. And Coq will attempt to fill it in. When I say attempt to, I'm speaking carefully. It will not always succeed. So it's using a unification-based type inference algorithm, just like your favorite other functional programming language. But because we're in a very rich and powerful and expressive language, there is no completeness theorem. There's no theorem that says if you take any untyped phrase that has a valid type annotation, that the type inference mechanism will find it. In practice, in situations like this, in situations where a functional programmer would naturally expect the type inference to work, it generally will. But notice that you're not restricted to, I'm not showing this in this example, but you're not restricted with underscore to using it in places where it's a type argument that you would expect an ML compiler or a Haskell compiler to fill in. You can use it for other arguments as well. You can use it to fill in numbers. It's just less likely that the type inference is going to be able to figure it out, because generally the number that you want is not going to be determined by unification. Occasionally it will be, and then you can use this underscore just as well in those situations, please.
Do you have a reference how the construction algorithm works? Can I look for it? And it seems.
Are there any experts left in the room that can speak to that? I don't know a reference for that.
It's not about Coq, but Conor McBride and Alan Gundry have a recent paper on tutorial higher order unification for the different types.
Okay, that's useful. So it uses higher order unification. The original reference on higher order unification is Huet from sometime in the 80s, which is actually quite readable. But there's a lot of black magic in the type synthesis, the argument synthesis stuff. Coq users understand it is in a quite rough and ready fashion. So just try it, see if it works. If it doesn't, fill in more. Okay, so we can fill in underscores anywhere we want. In fact, obviously, filling in the underscores themselves is a little bit annoying and heavy, and we would like to elide those, and Coq also allows that. So what we can do is we can say, if you look at the bottom of the screen, we can declare that the argument x to the nil constructor should always be inserted automatically. So every time Coq sees nil, it should automatically insert an underscore after it, and then attempt to do the inference. And indeed, we can be even a little bit more shorthand than that. When we introduce a function like length, if we put curly braces instead of parens around a type argument, that's an automatic declaration. That's equivalent to giving it with parens and then declaring afterwards implicit arguments for this constructor, for this function. Okay, it's worth knowing. Yes, sorry. That is the next point. So if we run implicit argument synthesis, we may occasionally need to turn it off again. So we need a way of doing that. Why would we want to turn it off again? Well, there are situations where the inference of the thing that replaces that underscore that's implicitly inserted may fail. For example, here's a canonical case. This is the one that you will trip over first. If we try to define a new version of nil, say, so define my nil to be nil, type inference will fail. Why? Because I haven't given a type for my nil. So unification has nothing to go on. Nil requires a type argument, but there's no local information determining what that type argument should be. Right? So obviously, or probably obviously, I want to define a more polymorphic one, or maybe a specific version that I have in mind. So there are different possibilities, but one way to do it is to nail it down. So to say, to give some extra information elsewhere that determines what the underscore must be, that's implicitly here. Another way to do it is to turn off the insertion of the underscore, and we do that with an at in front of the identifier that has the implicit arguments. All right, so you can write at nil of nat. Okay, now this is nice because using these underscores, we can now recover once again our brackets notation for lists. If you think about it, the brackets notation for a list with several elements has a lot of underscores in it. But the fact that we can ask for them to be inserted implicitly means that we can still write it just as brackets 1, 2, 3, close brackets, and all the types get taken care of by the type checker.
The notation for x, y, to me it looks like it's x has type y. Maybe.
This is a standard notation from the ML world.
Okay.
That's the way ML people write things. So now we can build up some, now we can redo some of the things that we did a little while ago in the monomorphic case. We can have polymorphic versions. So here are polymorphic pairs. So this type of pairs is parameterized on two types, x and y. We can have notations as usual. We can have functions like first and second. We can do the same thing with options. No big deal there. That's just kind of spinning out the consequences of what we did before. Coq is, of course, a higher order functional programming language, so it's a functional programming language that deserves the name. So we can write functions like filter and map and fold and all of those. So here's how filter looks. Nothing really surprising there at all. Here's how we can use filter, and there's nothing surprising here. The only thing to note is here's how you write an anonymous lambda expression. So lambda is written FUN, and then the dot is written with a equal greater kind of heavy arrow concrete syntax. Okay, here's map, the usual thing. Here's fold, the usual thing. So just standard functional programming. Okay, a little more interesting. So first of all, I have to put on my dog collar and give you a short sermon about the dangers of mindless hacking in Coq, which I'm sure you've probably already experienced. So it is very easy in Coq to get going with tactics and spend hours before you kind of stand back and look at the thing that you've been whacking away at and say, "Now wait a second, is that actually true?" So it's better to save yourself those hours. And so having said that, the temptation to simply try tactics and see if you can get the thing to go through, even without completely understanding what it's saying, is so strong that Coq experts do not resist it. Right? So if you see an expert driver of Coq in the middle of some big development, there will be many moments where he or she does not at all understand what the goal in question actually means. And they're just trying one tactic after another. And so my recommendation to you is it's okay to do that for 5 minutes. But if after 5 minutes you feel like you're not getting any place, then I would recommend looking at what you're trying to prove and seeing if you can understand it. If you have trouble understanding it, or if you kind of iterate a few times where you kind of think you understand it, try to go forward a little bit, get stuck, try again. If you go around the loop like that a few times, I would actually recommend putting the whole computer aside, getting out a piece of paper, good old pencil and paper, and trying to see if you can do the proof by hand, and kind of get an intuition for what the steps are. Because if you don't have a pretty clear, basically if you have tried just following your nose and gotten stuck, you may not get stuck, you may get to the end and it just works, then you're lucky. But if that doesn't work, then you probably need to actually understand it, and that's often best done with paper. So don't fall into the trap of just hacking. Is that an accurate characterization of New Perl, Bob?
Yeah, I would say, but if you watch drivers like Bickford, they are doing things in that mode where they don't understand the goal that just seem to work more often than for most people. So they've got some deep.
There is a certain magic to the hacking sometimes. That just develops as you use it. Okay. On with teaching you how to hack. So the apply tactic. I forget, have we seen apply already? Yes, a little bit. Okay, so apply is a tactic that takes some previously defined, either kind of locally defined fact, something that a local hypothesis that you've introed into the local environment, or a previously defined lemma that has a name, or a theorem that has a name in the global environment. So what does apply do exactly? It takes the fact that you're naming, the local or global fact, it tries to unify it with the goal. And if it succeeds, then it replaces the current goal state by what? Well, if the theorem is a non-conditional thing, if it just says this is equal to that, then it replaces it with nothing. It solves the goal. But you can also use apply with conditional theorems. So if you have a theorem in your context that says P implies Q for all some collection of variables that are free in P and Q, P implies Q, and your goal looks like Q, then you can apply that theorem, and what will happen is it will unify the goal state with Q to get bindings for the variables that are free in P and Q, and it will leave you with P as the subgoal to be proved. Or if there were several hypotheses, it will leave you with several subgoals that now need to be proved. Yes, sorry. Right, so what proof term is actually being built? Well, can you guess from the name? What's actually being built in the proof term that's under construction is an application.
Yeah, but I mean, how is it built? Is it mapped as well? How is applying defined?
Let's postpone that till Monday, because we'll come back and talk about proof objects in more detail. So for now, forget about proof objects. So I said the other day that what the tactics are actually doing is building a term. But let's forget about that and just look at it as a game of trying to get the subgoals to eventually go down to 0 and say QED.
Are the terms that they're building kind of built into like system, or
Yes,
are they
they are not just like, they're exactly the ones that you would
they're
write.
not more complicated?
Well, they are more complicated because we're tending to let's see. If you took the same theorem, like the currying or uncurrying theorems that we looked at, then the proof object would really look exactly the same. It would be the lambda term that was the answer to the exercise earlier in the week. For a more complicated theorem, it will be a bigger proof term, but built out of the same stuff. Okay. All right, the next tactic that I want to tell you about is called unfold. And this is used, let's see, shall I just show you this? Yes. Is it in the other file? Yes. Okay, so I need a faster laptop. This is the advantage of working with Coq. You can always tell your advisor you need a faster laptop, even if the one you have is only a month old. Okay, so suppose we were trying to prove this kind of silly fact. So plus 3 is plus partially applied to 3. That was defined someplace. I think we skipped over it. If 3 plus n equals m, then plus 3n plus 1 equals n plus 1. So it's just a silly little fact about plus 3. So if we do this intros, now we'd like to do a rewrite. But rewrite doesn't work here because the goal doesn't actually unify with the equality hypothesis that we'd like to rewrite by. Why? Well, because the way the unification works is